Hello everybody. Welcome to this mass-based pie cut and tubing change to increase C3 Corvette exhaust flow video. The purchased exhaust system you see in figure 1 was formed by the compression, or otherwise known as the crush method, which deforms round steel tubing into distorted and varying amounts of oblong or elliptical passages that introduces unneeded back pressure. Measurements of this purchased exhaust system, when compared to an identically shaped one without distortion, showed a reduction of effective tube area of approximately 10% at the most distorted point, which directly affects back pressure. The mid-length bend in the lower tube of figure 1 is also harmful to exhaust flow and is not needed except to apparently match the GM factory forming process. Well, I decided to increase the flow by replacing the deformed tube sections with round ones and eliminating the unnecessary mid-length bend. The first step was to measure each radius of curvature and bend's included angle of the purchase system, which were measured with a digital angle finder protractor. Figure 2 contains a collection of varying semi-size semicircle radiuses from 2 inches to 6 inches that were used to measure each bend's centerline radius as the average of the outer and inner bends. They varied from 4.75 inches to 5.25 inches. Apparently, the GM factory tooling was designed to produce 5-inch nominal centerline radiuses. That nominal value was used in all the following calculations. Since simple direct solutions of pie cut parameters were unable to be found in literature or on the YouTube particular outside the curve tube length to achieve a desired centerline radius, it was decided to develop the mathematical formulas to calculate the direct solution of each pie cut parameter as a function of the other 4 parameters for the replaced tube sections. Those selections are shown below. 5 examples that cover all parameters are also provided. The pie cut calculations parameters are the tube outside diameter, D, tube bend total included angle, theta, number of pie cut sections, N, tube bend centerline radius, R, the pie cut top length, L sub T, and the pie cut bottom length, L sub B. Here we have direct solutions for each of those parameters given the values for the others, the unknown 4 parameters. Note 1. The arctangent is the inverse tangent function normally found on scientific calculators or in a program like Microsoft Excel. It provides the angle that has a tangent equal to a given number. For example, the arctangent of 1 is 45 degrees because the tangent of 45 degrees is 1. That's all we're going to delve into trigonometry for the time being. Note 2. L sub T is the tube length of the pie cut top. It is used in setting up the cutting equipment device. The calculated pie cut bottom length, L sub B, will automatically result if the cutting equipment device angle is correctly set. Example 1 here shows the pie cut top and bottom lengths for 3 different scenarios. One is for a 22 degree bend with 2 sections and a centerline radius of 5 inches. The second one is for a 50 degree bend with 4.5 sections and a centerline radius of 5 inches. And lastly, for a 45 degree bend with 4 sections and a centerline radius of 5 inches. Note, A whole integer number of sections, for example 1, 2, 3, 4 or whatever n, means all pie cuts have two equal half angles as shown in figures 3 to 4 which are coming. A partial integer number of sections, such as for 50 degrees above, with 4.5 numbers of sections, means there are a total of 4 double half angle sections and they're equal, but one section has only a single half angle as shown in figure 5. Figure 3 is here shown graphically for a 22 degree bend with two sections. Both L sub T, L sub B, or the pie cut top and bottom sections, are solved directly. All you need to do is to plug in the values for the unknowns on the right of the equal sign, and you can calculate the values of the pie cut top and bottom sections to aid in cutting your tubes. Figure 4 shows a graphical representation for a 45 degree bend with four sections, again solving for the top and bottom pie cut sections directly, given the values for the other four unknowns. Figure 5 is for a 50 degree bend with 4.5 sections. Again, direct solutions for the pie cut top and bottom sections. Note, this number of sections was chosen in order to have a pie cut top length very close to the values obtained for those of 2 and 4 sections. That will enable all pie cuts to be made with the same cutting equipment setup. There is nothing special about the value of 4.5. Different pie cut top lengths would require a different number of sections. Example 2 here shows the calculation for the centerline radius for a 2.5 inch diameter tube, a 22 degree bend, two sections, and a pie cut top length and bottom length of 1.204 and 0.722 inches. As you can see below, there's for the other two scenarios. Example 3 shows calculations for a tube degree bend of 2.5 inches, two sections, centerline radius of 5 inches, and pie cut two. Well, that, yeah, they're just repeating it, but now we're calculating for the theta, for the included angle. And here we calculate the number of pie cut sections for the number of sections given the values for the other four variables. And here we have direct solutions for calculating the diameter of the tube in case you want to double check to see how close your other parameters are to the direct solution requirements. This is all you need to calculate the pie cut top and bottom lengths for your cutting equipment. Instead of wasting tubing or wasting time or eliminating additional expense for setting up and cutting, recutting tube lengths, you can solve directly for their values and set up the equipment accordingly, knowing that you're going to come out with the right angle, the right radius, and that's important. So I hope that this mathematical approach will help you in your projects. Thanks for your interest and good luck with your projects. Goodbye.